All right, folks, we are now going to get into other aspects of inverse functions. So we looked at how we can show we have inverses or verify that we have inverses algebraically. So if we compose them within each other, both directions, they should cancel out to equal x. And that verifies that they're inverses. But how else could we do that? And another way is to look at the graphs. So, and we're going to see that there's a relationship there as well. If we reflect the graph of a function in the line y equals x, then we attain the graph of its inverse. So we showed in the last video that these two functions are inverses. We showed it algebraically, but let's take a look at the graphical side of this as well. Now, if we wanted to analyze this function here, as far as the transformations that's going on, what would we say? Well, the one in front is deceiving, potentially, because normally we see vertical shifts at the end of the function, but they can be put into the front. So that one, that plus one, is telling us that it's going up 1 unit. So this is going up 1, and then the minus in front of the entire function means what? That's going to be a reflection in what? The x or the y? Remember, if you negate the entire function, it's a reflection in the x. So let's draw that one out and see what it looks like. So we have x cubed as our parent function, so we know that kind of comes down and goes through something like that. But we have these transformations. So if we went up 1, now I like to do reflections in the x first, because if you reflect it in the x afterwards, it might mess up that shift. So let's flip it in the x-axis first. So it's going to come down through and then come down. But then we have to move it up 1 unit. So the origin gets moved up 1. And then remember from before, we had 3 points. So the origin and then these 2 other diagonal points. So when we draw this, it's going to go down something like this. I'm having a hard time drawing, so. But there is a rough sketch of our function f. So now we want to see function g. So what transformations are going on here? Now we got to be a little bit careful because of this backwards relationship. Now remember, if we rewrote this a little bit, it might help identify those transformations. So the first thing we could do is rewrite it as negative x plus 1. But then, remember, we want to affect x, not negative x. So let's factor out that negative sign. So negative x minus 1. And so now we can see what's going on. So this minus 1 here is a shift which direction? Hopefully saying to the right. So this is going to be going to the right 1 unit. And we have a reflection in the y-axis. So our parent function is the cube root of x. So remember, that kind of comes down from over here and it comes up, up, up through the origin and then off to the right. So, okay, let's do that reflection first. So if we reflect it in the y-axis, it's now going to come from this direction and down, but then it's going to be shifted to the right 1 unit. So this one's a little clunky, but we actually have 3 points for this one as well. So it's going to be coming over, come down through this point. Now it's going to be very, very close to that curve in there. It might not be exactly on top of it, but it's going to be very, very close to it. Excuse me. But this is what we have for our pictures. our two functions f and g. Now, if we put in our y equals x line, and you can kind of see it here. Now, all we want to do is just pretend that we're going to fold them right on top of each other. Fold it right across, and you can see that it's going to land right on top on both cases. So this will give us inverse functions. So this is another way that we can, this is another tool in our toolbox of verifying that we have inverses. So we can do it graphically, we can do it algebraically, but how can we even get the ball rolling to begin with? How do we know we even have the possibility of getting an inverse function? And that goes back to some analyses of that function. And one of the things that we're going to need to see happen is that it's 1-to-1. So what is 1-to-1? Well, 1-to-1 is when each value of the dependent variable corresponds to exactly one value of the independent variable. A function that has an inverse, a function f has an inverse if and only if f is 1-to-1. Additionally, if for elements a and b in its domain, f of a equals f of b implies that a equals b. So the big part of this is that tail end piece. If we have two y values that are the same, that should guarantee that those x values are the same. There can't be more than one possibility that gets us to those y values. So very similar to what we saw for functions. So let's see if we have some 1-to-1-ness going on. So let's say we had g of a equal to g of b. Now, the result we want to end up with is that a equals b. Now, the name g doesn't mean anything. It's just those are the y values. We want the x values to be the same. So if we plug this into g, we'd have a over 8 equal to b over 8. Okay, so that's the first substitution. So now, how could we algebraically or mathematically get to a equals b from this statement? Well, mathematically, we can multiply both sides of the equation by 8. Now, we're not changing the value of the equality at all. So now, if we cancel those 8s all out, we do end up with a equals b. So, yes. All right. That one wasn't too bad of a function. Let's try a little more complicated one. So we want f of a equal to f of b. Let's substitute it into the function. So we have the square root of 2a plus 3 and the square root of 2b plus 3. So now, how do we break this down, legitimately, mathematically, legitimately? What would be the first thing that we should do to start to break this down? Answer should be those square roots. They both have square roots. If we square both sides, that's a legal move that we can take. So that's going to get rid of those square roots. And now, what would be the next step? Mathematically, we would subtract the 3. 3's can get gone. Get gone, there's some good English. And then finally, the 2's can go by dividing both sides by 2. So this one's also a yes. What about x squared? Well, let's do it the same way. H of a equals h of b. So substitute, we get a squared equals b squared. Now you might say, square root, right? Yeah, we're going to square root them. And so a equals b. But not really. A could be equal to b, but a could also be equal to negative b. It could be equal to a to b or negative b. If we squared each of those, we'd get back to b squared, which is the same as a squared. So either one of those would be a possibility. So a could be equal to two things, and there's the problem. So, and we could go even further if we wanted to. We could say, well, negative a is the same problem. It's equal to b or negative b. So in either case, we got a mess. It's not one thing equal to one thing. So this is a big no. It's not one-to-one. So anytime you have that happening where two x values get you to the same y value, that's a no-no for one-to-one. Just the opposite for function stuff. So, all right. So what about number 5 here? Now we're getting a little bit in length of time, so let me just take a quick peek and see what's left. And I think what I'm going to do is hold example 5 for the next video. Bummer, right? So stay tuned for the next video and we'll wrap up this section.